Welcome to this special lecture about, which I'm going to do a lecture on fun with Fibonacci numbers. That we'll use a power series with coefficients being the Fibonacci number and learn interesting things about them. And it will also be instructive from the point of view of Laurent expansions and properties of power series. So I saved it for this special eclipse day just because it's a fun thing to do. So let me pause and go over to my tablet PC here. Okay, you see there what we had before. Those are the those are the Fibonacci numbers. They start out with 1 and 1, and the next one would be the sum of the previous two. So A2 is 2, A3 would be the sum of the previous two, which is 1 plus 2. So another way to say what they are is A0 equal 1, A1 equals 1, and then after that, AN is the previous one plus the one before that. And that's starting at N equals 2. And what we did earlier in the semester when we were studying these things, we wrote a function, f of z, which is a power series whose coefficients are the Fibonacci numbers. And the thing we did when we did that was we wanted to analyze what the radius of convergence of that power series was. And an example where all the basic tools we had didn't really help us because we don't really know what all those ANs are or how they behave. So the trick here was to assume that this thing converged. We don't know that it does. So we assume the radius of convergence of this thing is r bigger than 0, so that f is an analytic function. We don't know that's true, but we'll experiment and see what happens. Okay, so what did we do? We realized that recursion formula for the Fibonacci numbers implied that f of z equals 1 plus z times f of z plus z squared times f of z. Okay, I did this early in the semester carefully and worked out all the details. So if that thing does converge to an analytic function, it would satisfy that equation inside the radius of convergence. And you realize, oh my gosh, I can solve this for f of x, and we get f of z rather, we get f of z equals 1 over 1 minus z squared, which I prefer to write as minus 1 over z squared plus z minus 1. And fascinating thing about that thing in the denominator, the zeros are famous numbers that come up in talking about the golden ratio. The zeros of z squared plus z minus 1 are, let's say, root 1 and root 2 equals minus 1 plus or minus the square root of 5 over 2 when you do the quadratic formula. And let's see, the famous number R1, let's take R1 to be the famous one. That's minus 1 plus the square root of 5, so that's a positive thing in the numerator there, over 2. That's the famous golden ratio number. And let's take R2 to be equal to the negative 1 minus the square root of 5 over 2. Then, fascinating thing is that we can go backwards now. Now that we have this function that has a power, that thing has a power series, and we see that this f of z has this function has a power series with a radius of convergence equal to the distance from 0 to the nearest place where it has bad behavior. It blows up at those two roots. And if you think about where those roots are, the R1 would be the closest of the two to the origin. And then R2 is out here, and it's more negative. Okay, so the radius of convergence for this power series would be this radius. And I'm going to do something interesting later in the lecture here. This thing is also going to have a Laurent expansion in these various annular regions inside between the red one and the green one, there's going to be one Laurent expansion. Outside of the green one, there's going to be a Laurent expansion. And inside the red one, it's going to be a power series. Okay. But here's the fantastic thing we realized. Now that we know that this function, the rational function, has a radius of convergence. So let's see the rational function. What was it? It's -1 over z squared plus z minus 1 has radius of convergence equal to R1, the golden ratio. And now that we know that we know it has a power series. Summation bn z to the n from 0 to infinity that converges. And then if we write out the algebra equation, it would show that the identity, let's see, I should call this rational function something. This is a rational function, R of z. Okay, it has a power series, and R of z satisfies that same identity. R of z equals, let's see, it'd be 1 minus z times f of z minus z squared times not f of z, R of z. Minus z squared R of z. And before we were looking at this as a consequence of the recursion formula. Now when we look at it, the aha moment is the coefficients of R that satisfy the recursion formula for the Fibonacci numbers. And so that means that the BNs are equal to the ANs, the Fibonacci numbers. And now we can claim with certainty that the power series we started out with does have radius convergence, the golden ratio. Okay. So that's all done. We did that already. The exciting thing I want to do today is do a little more work and find the power series using simple facts about geometric series and figure out some interesting identities. The most interesting thing today is going to be that the Fibonacci numbers are given by a formula, namely 1 over the square root of 5, 1 plus the square root of 5 over 2 to the n plus 1 minus 1 minus the square root of 5 over 2 to the n plus 1. That's hard to imagine, but we're going to show that. And so even though this looks like there's square root of 5s all over the place, when you actually crank those things out, all the square root of 5s cancel out somehow and go away, and you're left with an integer, which is the Fibonacci number. So it's kind of a shocking formula, hard to believe. Okay, so the key here is we have our function we started out with, minus 1 over z squared plus z minus 1. And I found the roots of that thing in the denominator. That's minus 1 over z minus r1, the golden ratio number, and z minus r2, the other one. And I want to find the power series expansion for that using geometric series. And so we kind of did some problems like this in the homework. I can do partial fractions and write that as a over I don't know, z minus r1 plus b over z minus r2. So that's partial fractions. And when I find out what those a's and b's are, I multiply through by the quadratic thing, z minus r1 times z minus r2. That would give me a minus 1 on the left. And it would give me an a times z minus root 2 plus b times z minus root 1. Which if I write out is, let's see, that would give me a plus b times z. And then I'd get plus a constant term of minus r2a minus r1b. And if those two things are going to be equal, this constant term would have to be minus 1, and this would have to be 0. A plus b would have to be 0. And so, let's see, that's going to tell me that b is equal to minus a. So if I put that now, that the first equation there tells me b is equal to minus a. And when I stick that in the second equation, I would get minus r2a minus r1b, which now I know is minus a, is equal to minus 1. And so that's going to tell me that what? A is equal to what is it? Minus 1 over r1 minus r2. Okay, let me continue messing around with that. That's equal to minus 1. Remember, r1 was minus 1 plus the square root of 5 over 2 minus r2, which is minus 1 minus the square root of 5 over 2. The 1/2s cancel, and I get a is equal to minus 1 over the square root of 5. Simple. And so from up here, the previous box for b, I get that b is equal to minus a is equal to plus 1 over the square root of 5. That's neat. And so now I have a nice formula for my function in terms of simple things. F of z is equal to 1 over the square root of 5. Let's see, 1 over z minus root 2. That was the positive one. And the other one is minus 1 over z minus the famous root. And now you say, well, how could I get a power series from this? And the easy answer is when we prove the Cauchy integral formula, we played around with something exactly like that in the Cauchy integral. And the idea was, let's see, I go back to that picture. I would have a small circle of radius r1, a bigger circle of radius r2. That's pretty bad. Okay, so here was r1. Here's the origin. And I'm taking my z, my r2 is a bigger negative thing. Oh no, r2 was way over here. Bigger negative thing. There was nothing right here. Okay, my z is inside this, I'm going to do the z case inside the smaller circle at the moment. So that means that the z has a smaller modulus than r1. So if I divide, I want to so I'll take care of this first one here. Let's, I'll write this one as 1 over z minus r1. I'll divide the top and the bottom by r1. In fact, why don't I I'll multiply top and bottom by minus 1 over r1. Then I would get, on the bottom, I would get, it looks like it's the limit of a geometric series, the sum. And I would get 1 minus z over r1. That's what I was shooting for, like in the proof of the Cauchy integral formula for power series. We got power series that way. Okay. And on top, I get minus 1 over r1. And now I can mess around with that thing and realize, aha, that since mod z over r1 is less than 1, so that thing is actually the limit of a geometric series. And the geometric series would be minus 1 over r1 times 1 plus z over r1 plus z over r2 squared, not r2, r1, plus dot, dot, dot. And I can do exactly the same thing with the other rational term in the partial fractions. So in fact, I get the same thing, do the same thing for the plus 1 over z minus r2 term. And so when I do that, I get that my function is 1 over the square root of 5. Okay, this one would be 1 over, the first one would be 1 over r2, 1 plus z over r2 plus z over r2 squared, etc. And the other one is minus 1 over r1, that stuff up there, 1 plus z over r1 plus dot, dot, dot. And now I can combine those two and get the power series for F. Let's see. And now it's just algebra. So what would I get when I do that? I would get 1 over the square root of 5 in front, I would get, do I want to do that? Maybe it wouldn't be that much fun. So combine these to get the famous formula that I started out writing. It's just some algebra. And so we found a power series of a rational function just by playing around with geometric series. And interesting, we know that f of z has a Laurent expansion in the annulus in the annular region. Let's see, that would be the annulus where the radius goes from R1 to absolute R2. R2 was negative. And here's how we can find that using just the geometric series facts we have. So, we had these integral formulas for the coefficients. So here's a nice trick. When you have something explicit here, nice trick to find the coefficients. So I don't have to use all those integral formulas and play around with the residue theorem. It would be kind of excruciating. So let's see, remember my function is 1 over the square root of 5. I'll put the 1 over square root of 5 in front. 1 over z minus root 2 minus 1 over z minus root 1. And now I'm in this annular region, so I have that R1 is less than the modulus of z is less than absolute R2. Okay, so now, let's say if I want something that's less than 1, think about what I'd have to do. R2 is bigger than the modulus of z right now. So I should multiply 1 over z minus R2. I should multiply the top and the bottom by 1 over R2. No, is that right? No, 1 over z. Then I would get 1 over z on top. And here I would get 1 minus R2 over z. And I did that because, oh blast, I did the wrong thing. That was dumb. That's what I should have done to the other one. So here's how you realize you made your mistake. I want to make that thing less than 1, so it's a geometric series. So this is one I should do like I did previously. And it'd be a power series, same as before. I get minus 1 over R2 on top, and here I'd get 1 minus z over R2. And the good news is that's less than 1. The modulus is less than 1, so this is a geometric series. And so it's the part of the Laurent expansion that looks like an analytic thing. That's just a geometric series. Okay, the other one's more interesting in this case. And let's think about it. this term is 1 over z minus r1, and my modulus of z is bigger than r1 now. And so this is the one I should have multiplied by 1 over z over 1 over z. And so that's equal to 1 over z on top. And on the bottom, I get something that looks like the limit of a geometric series, r1 over z. And the reason I chose the thing I did is that the modulus of that thing is less than 1. Check. Okay, and so now I can play the usual game and write that as a limit of a convergent geometric series. Notice I have a 1 over z in the front now. That's 1 over z times 1 minus r1 over z. Oh no, plus 1 over r1z plus 1 over r1z squared plus etc. And so I could write out the coefficients now. And notice I get all these negative terms. I'd get a 1 over z plus r1 over z squared plus r1 squared over z cubed plus, that looks like, those are the negative terms in the Laurent expansion. And these are the ones on this side, that's with regular old power series. These are the positive terms. In the Laurent expansion. And here's an interesting thing to consider. You might say, oh my gosh, this function has an essential singularity. Well, you'd be wrong to say that because the essential singularity business only holds at an isolated singularity. So the fact that this has infinitely many negative terms is meaningful in the when it's in the inner circle where the function has an isolated singularity, but not terribly meaningful, in fact, not meaningful at all in the annular region between R1 and absolute R2. And so the last thing to do would be to find the Laurent expansion outside the disk of radius absolute R2. Then the only thing I would change is when I deal with this one, I do the same thing with the 1 over z for the other term, but now then I would also do a 1 over z on this term. And I'd get two of those things. I'd get a 1 over z on top, and then I would get 1 minus r2 over z. And I'd get infinitely many negative terms for that one too. So I'll just say et cetera there. Once you do it a couple times, it becomes routine. Interesting thing is the Laurent expansion is different in all three regions. And you sort of have to use different tricks in different regions. By the way, I guess I should remark that this basic technique can be used to find the Laurent expansions same methods. To get Laurent expansions for any old rational function. Okay, you remember that but you need one more fact. I'll say what you need. You know, when you get partial fractions, you might get terms like a over z minus root, but you might also get terms like a over z minus root squared, or a over z minus root cube, etc. And so you have to do this same trick for those. And so I showed you how to deal with this one. Check, we know how to do that. But how would I deal with the second one if I was going to try to find its Laurent expansion? Well, let's see, here's the key. We know that 1 over 1 minus z is equal to 1 plus z squared plus blah, 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 when the modulus of z is less than 1. And we also know that we can differentiate power series term by term. So when I take d by dz, it would differentiate. Then when I differentiate this one, I get minus 1 over 1 minus z squared times minus 1 would make it a plus 1. So that would be the derivative over here. That would be z plus 2z plus 3z squared plus dot, dot, dot. And that's how I would deal with I guess I should do it one more time before I get, let's see. Here's how I would deal with a over z minus r squared. I would multiply the top and the bottom by 1 minus r squared, or minus, let's see, that'd be a over z minus r squared. I'd multiply the top and the bottom by 1 over r squared. Then that would be a over r squared on top, and here I would get 1 minus z over r squared. And then I could use this. I would use that if mod z is less than r. If mod z is greater than r, then I do the other trick. And the other trick would be I multiply by 1 over z. And that would give me a times 1 over z on top, and 1 minus r over z squared. If r is less than the mod z. And then I expand it and get something that looks like a Laurent expansion. I would get negative terms of Laurent expansion. Etc. And then if I realize, oh, if I had even bigger powers, I can just keep differentiating that geometric series term. And for example, the next time I would get 2 over 1 minus z cubed would be equal to 2 plus 3 times 2 times z plus 4 times 3 times z squared plus etc. for the higher order terms. Okay, that's the fun part that I wanted to show you today about Fibonacci numbers and how they're related to power series manipulations. There was one more thing I wanted to mention today, and that is a fact I sort of skipped when we were doing power series. The fact is you can multiply power series like polynomials. And the demonstration of that turns out to be quite straightforward. Let's suppose I have a f of z is a summation a(n). Let's take the power series centered at the origin, just to make it easy. And g of z would be a sum of bn z to the n. And let's let h of z equals the product of those things. Then h of z has a power series. H of z would be a summation of cn z to the n from 0 to infinity. And the radius of convergence of that, of course, would be, let's see, the radius of convergence of h is greater than or equal to the minimum of the radius of convergence for the f power series and the radius of convergence for the g power series. A miracle can happen and it could be much greater, but it's guaranteed to be greater than or equal to the minimum of those two. Because we know that because we know power series converge to analytic functions. So the minimum there, we'd have f and g both being analytic on that circle, inside that circle. And so h would have to be analytic inside that circle, and its radius of convergence, therefore, is bigger than or equal to that radius. Okay, that's the easy part of the fact. The interesting part about polynomials is the coefficients c sub n are given by same formula you get when you multiply polynomials. So let's see, that would be a naught times b sub n plus a1 times bn minus 1 plus a2 times bn minus 2 plus dot, dot, dot. The last one would be an times b naught. And those things, those coefficients add up. So k goes from 0 to n, ak bn minus k. And so you notice that, the k and the n minus k add up to n. And so when you think about why that makes sense, is because you'd have here ak z to the k times bn minus k z to the n minus k is equal to, the powers add up, right? And so here we would get, when we'd get that this is a z to the n coefficient. And that's all possible ways to get a z to the n coefficient when you multiply the terms of the power series. Okay. And a fun way to prove this is to use Taylor's formula. So the proof of this fact, Taylor's formula plus the famous formula called Leibniz's formula, which is about okay, so Leibniz's formula is that it's about taking derivatives of products. So here's Leibniz. It says that the nth derivative of a product is kind of like a binomial expansion. It's a sum as k goes from 0 to n of n choose k times f to the k, f derivative, kth derivative, times g, n minus kth derivative. And you can prove that by induction. It's a fun exercise to do that. And so now when I apply that to the Taylor's formula, Taylor's would be that the Cn coefficient would be the f times g. This is an nth derivative here. Fg nth derivative at, I could make it a, but we're doing 0, so divided by n factorial. And so that would be equal to that thing above. I have to write it again. Let's see. Sum as k goes from 0 to n. Let me write what n choose k is. It's n factorial over k factorial times n minus k factorial times kth derivative of f at 0 times g n minus kth derivative at 0. Oops, and I forgot to divide by the n factorial. So I have to divide this mess by n factorial. That just gets rid of the n factorial in the numerator. And then you realize, aha, this is when I cancel out that n factorial, this is just the kth derivative of f at 0, and I'll distribute the kth factorial under that one, and then I'll put the n minus k factorial under this one. And that's when you realize, that's just Taylor's formula. This is the an coefficient, and this is the bn, let's see, that's the ak coefficient. And this one is the bn minus k coefficient. And so it's a snap. Okay, that feels like enough to do on Eclipse Day. Thank you for tuning in so long.